Okay. So you guys sick of torsion? You're done with torsion? We're done with torsion? We're done with torsion. Well, we're going to see torsion again in your quiz, in your second quiz. But for now, I guess we can just forget about torsion for a little bit. And today we're going to start something new, bending. So I did tell you that this class is kind of like going along in axial loading, then it goes up in torsion, and in bending is bends up, right? So you got to stay with me in bending. So what we're going to do today for bending is essentially the same thing that we did for axial loading and torsion. Today we get into bending in easy steps. So we're going to do like the simplest case of bending today. And then on Tuesday, I'm going to hit you with the killer class with all the differential relationship and everything else. But today, you're happy about that. But today, we're just going to start easy and get into bending, just basic concepts. Okay? So, and by the way, I'm going to assign your 6 problem set today due next week. And this is the last one that you actually need to turn in. There is a 7 problem set that you're not going to have to turn in. You're responsible for the work, but you do not need to turn in. So the good news is that this is it in terms of material that you need to turn in. The bad news is that the next one you don't turn it in, but you still have, you still have to understand and be able to do those kind of problems. Okay, so I will post that one today, and I think we're all set to go. So beams in bending. So what happens now is that we are still sitting in the xy plane. So we still are in the xy plane, and we still have a wall. And on the wall, we have something that looks very familiar. A long, slender bar. And now, instead of calling it a bar, like we called it in axial loading, and instead of calling it a shaft, like we called it in torsion, we're going to call it a beam. So now this one is a beam. And in 201, we do slender beams. We do beams in which if you have a length of the beam, L, and if you have a height of the beam, H, so for now, let's imagine a rectangular beam, or it can be a circular beam, but it's going to have a certain height. So the height of the beam is smaller, much smaller than the length. So the beam in 201 are slender, which means that H is much less than the length of the beam. Okay? So you're saying, okay, how is this different from a shaft in torsion or a bar in axial loading? What is different is the way it is loaded. So for torsion, we were saying, let's consider the possibility of torsional loads, so torques, along with the axis of the rotation of the torque along the axis of the shaft. That's torsion, right? Now we're thinking again about moments, torques, but instead of being torques along the axis of the shaft, we're going to have the axis of the moment orthogonal to our xy plane. So we're going to load it with something that looks like this. I go there, and I twist the end. So if this is my long, slender bar, that is a beam, it becomes a beam when I go to this end and say this is a wall on this side. I go here, and I am applying a torque. But the torque with the axis of the torque, with the right hand, the axis of the torque comes out of the plane where the problem is. So the beam is in the plane. The axis of the torque is out of the plane. You see? So in this case, I'm applying a concentrated moment at the end of the beam. How do I do that? Well, I could, for instance, pull a little bit at the bottom and push at the top, right? I do what I do with my hands right now. The bottom of my hand is pulling. My fingers are pushing in. I'm giving a moment with an axis coming at you. You see? Okay.
H is the thickness of the beam?
H is the thickness of the beam, the height of the beam. And it's small, so that the beam is long and slender. So this moment, the difference in nomenclature is that, these moments and the torsional moments, they're moments, concentrated moments. But we tend to call them torques in torsion, and we tend to call them bending moments in bending. Okay? So normally we use symbols like M for the bending moment that apply to this beam. Okay, so I'm applying that bending moment. Let's call it M0, just to remember that is something. The units are the same as the units as torque. That is Newton times meter. I'm applying 3 kilonewton times meter at the end of this beam. Okay. And we are interested in what happens inside the beam. Now, the other simplification that we do in 201 is that the beams are slender, and also the beams that we deal with in 201 are symmetric. What that means is that if I look at this side, so if this is my x-axis and this is my y-axis, the z-axis will be coming like that out of the board, right? So if I look at the cross-section of the beam, symmetric in 201, the symmetry is both up, down. So if this is my z-axis and this is my y-axis, and now x comes at 2, so this is the beam. I want beams that are symmetric left to right and up to down. So all the cross-sections that we're going to deal with in 201 are cross-sections that are symmetric. I can make them symmetric with more complicated shapes. So this is allowed because it has 2 axes of symmetry. See? Anything which is symmetric, up, down, and left to right is allowed in 201. This is okay. This is called an I-beam. This is okay. This is a rectangular beam. This is okay. I can make beams that are thin like that. I can make it, flat on the other side. Anything which is symmetric about these 2 axes is okay. So is up, down. The symmetry is up, down. And also left to right, both of them. Okay? By taking this simplification of the symmetry, we're going to be able to cut some corners, essentially, in the treatment of bending. Okay, so I'm applying the bending moment at the end, and now what I'm interested in is what does the beam feel inside? What is the resultant inside the beam, right? For axial loading, we were always going after our axial force resultant. And for torsion, we were looking at our torque resultant. Now in bending, we want to find something inside the beam that balances this applied moment from the outside. So if I cut the beam here, I do my good cut, and I isolate this part here of the beam like that. And if I'm applying an M0 here with the axis coming at you, in order for this beam, this part of the beam, not to start spinning along Z, right? This thing can just, if I apply a moment like this can just start spinning in the plane. You see that? To prevent that, I need to balance it with something that is inside. So there must be some resultant of the stresses inside the beam that balances this M, right? That is what is inside the beam, what is caused by the stresses in the beam, what is carried by the stresses in the beam, connected to the deformation inside the beam. This is our curly guy. So,
Is that what we're saying?
So this is the curly guy inside. First we decide what to call it. So we call it M, curly M. How creative. Another curly guy. Curly M, and this is the curly M is the bending moment resultant. And see, because I taught you to think about directions and conventions, right? So the first thing is like, which way do you draw it? Well, it must have its own convention, the same way as N had its own convention. For N, we said that the axial loading is positive if I pull on the bar so that it gets longer. If the bar is in tension, N is positive. For torsion, we said if we twist it like that with the axis of torsion coming out from one end and coming out from the other end, that's a positive torsion. For bending, bending is like a happy world. For bending, things are positive if they smile. Okay? Think smiling. M is positive if it makes the beam smile. That's a positive M, of course. It's positive, happy. Okay, so again, when you do the moments, you see that the same way as when you do the axial forces, left and right balance out. So that is a positive. I cannot do my curly things today. This is a positive axial force, right? So pulls on one side, pulls on the other side. A positive moments, they also balance out. So you draw it like this on the right side if you cut on this end. If you cut on this end, you draw it like that. The same way as for axial loading, if you cut on this end, you draw it coming out. If you cut it on this end, you draw it coming out. For bending moment, you draw it so that it makes the beam smile in the XY plane. Okay? I'm doing this smiling, but really what I'm doing is, if the axis comes out of the beam, and that's your Y, positive is again coming at you, so that's the positive M, okay? So it kind of goes with this kind of ideas. But for now, forget about this kind of concepts. What I want you to think is positive bending moment, smile. So see how I drew it here? I drew it positive because I do not know how much it is yet. So how do I find it?
Sum of moments is 0.
Exactly. As simple as that. I use equilibrium. I do sum of the moment, and now the moments are moments z equal to 0. So if I sum of the moments z equals 0, and I have only concentrated moments, so I don't need to worry about the pivot, that is, so now z, moment z, very important. See this guy z? The same way as when I sum the forces in x, I project all the forces in the x-axis, right? When I sum the moments in z, which is at you, z is at you, I must sum the moments in the z-axis. So the positive z moments are counterclockwise. So z, remember that z is positive that way, coming at you, because this is your axis x, and this is your axis y. So the z component of the moment that gets into here is positive coming at you. So you have these two conventions. This is for the resultant, positive smiling, and this is for Cartesian. Let me get rid of n. We don't need n anymore. And this is the Cartesian positive, right? So you have internal resultant smiling, Cartesian components, positive in the plus direction. So if I do sum of the moment 0 here, I find sum of the moment in z are equal to 0, and that is m0 is plus or minus in z? Positive. M0. And then I need to sum this guy. This guy is positive or minus in z? Negative, right? If I do that, my thumb gets squashed into the board. So I have m0 minus m equal to 0. So I get simply that my bending moment must be equal to m0. Of course, must be equal in magnitude. If this is 3 kilonewton meter this way, this better be 3 kilonewton meter this way to keep the beam in equilibrium, right? This Cartesian thing also comes in when I want to find the reactions at the support. So for that problem here, if I want to find the reactions at the support, what do? I take the beam, I isolate it, and I say this is the moment that this is applied, m0. And now I want to know what this wall was doing. Here is the wall. The beam is attached to the wall here. Okay. To find what the wall does, I take away the wall, and I need to replace the wall with what the wall was doing, right? So the wall can give you reaction force, R, we did Rx in axial loading, it can give you reaction torques. So when we were doing torsion, our reaction torque that we were worried about is the component X of reaction torque. Of course, now that we're worrying about balance of moments in the Z direction, we're worried about the Z. So we want the TZ at A. Remember, R are reaction forces, T are reaction moments at the supports. We did TX for torsion. We do TZ for bending. We still call it T. These are the Z component of the same vectorial quantity, the torque at the support. Right? So this is TZ and is a Z component, so we draw it positive with the Cartesian. So if I draw it here, I need to draw it like that. So this is my TZA, positive, coming at you. Okay? So simple as that. If I do this sum of the moment Z for this free body diagram, I find the bending moment. If I do the sum of the moment Z for this diagram, I find that the sum of the moment Z is equal to 0 is equal to M0 plus TZA. So I find that TZA is equal to minus M0. So I find that my TZA has a minus sign, which means that in reality, it must go opposite to the way I drew it. So my solution, no real big surprise, tells me that if I apply M0 here, the support must also give me M0. And the fact that I find it with the minus signs means that the reaction at the support was going opposite to the positive sign convention. Okay? This is really straightforward stuff, right?